Hello and good evening, guys. So, uh, did you face any problem in solving the last week's assignments? I mean, week 4 assignments. So we'll first go through some of, not some, all the assignment questions from week 4. And once done, we will take up some problems out of the week 5 content. Okay. That will help you solve the current week assignment questions as well as uh, develop your understanding of the subject matter and help you in your exams of the current course as well as your semester exams. So talking about the last week's assignment, I will just share my screen with you. Yeah. So this was your assignment 4, and we'll take up the questions and with a little explanation of the answers, so that if you had any doubt, that gets cleared. So the first question said, the mold metal interface shows what? So what is the thing is, when there is a casting process and you are pouring in molten material into the mold. The molten metal comes in once it comes in contact with the mold well. There are there is a change in temperature, right? So, as in when the molten metal is poured, it starts cooling and solidifying. So there is, of course, a decrease in temperature when it comes in contact with the mold surface, mold wall, because the mold is in room temperature, right? And the molten metal is at the pouring temperature, or if you give a superheat, it is at a superheated temperature. But still, since the mold wall is in room temperature, once it comes in contact with the mold wall, the temperature decreases at the interface, right? So that's what answers this question. Now, in the second question, we have dimension of riser depend upon which of the following conditions. So that is A by V. That is the parameter you calculate, right? So A by B for riser must be less than that of the casting for in case of a riser design. We have seen such problems last week, right? So option A gets be the correct answer here. And now we have one numerical which says you have to determine the solidification time of a sphere shaped 18 centimeter dia casting of cast iron when it is poured with no superheats. Okay, so your effective latent heat of fusion is equal to the actual latent heat of fusion, which is 272 kilojoule per kg in this case. Now, the initial temperature is given to be 28 degrees centigrade, and the data is given in bracket as shown. So, we have already calculated that for a sphere, the non-dimensional constant beta, we have shown it last week. So beta happens to be lambda into 2 by root pi plus 1 by thrice of beta for a sphere. Okay, if it was a cylindrical casting, we should have 4 beta here, but it's a sphere, so we have a 3 beta. Okay, so V by A, the modulus of casting is given to be R by 3. You know how to find that, right? So volume is 4R cubed by 3. You divide it by 4 pi square, and the ratio comes up to be R by 3. And then you know how to find the non-dimensional constant lambda that is derived from the actual uh, equation for solidification time in case of sand casting. Yeah. So from that, actually, we find out this non-dimensional constants, lambda and beta. So lambda happens to be this del theta. F is the theta, F is the freezing temperature, and theta naught is the room temperature. So that way, you divide it by the melting molten metal density and the effective latent heat, which in this case should be equal to the actual latent heat only, 272 kilojoule per kg. And then you multiply this to the rho c for the mold, right? So that way you find lambda, you put lambda in case of beta, and you get a polynomial equation, right? So when you solve that equation, you get the value of beta. You should, of course, ignore the negative root. So you have only 1.75 as the beta value. Okay, now you put the value of beta in this equation, which gives alpha multiplied by the solidification time as the mold constant uh, square square into divided by beta square. Okay, so from that you have in this equation you have beta, you have alpha, which is thermal diffusivity determined by K by rho c, and rho c for mold has been given in the question, isn't it? So c is given, and then rho is given as 1600 kilojoule per kg per meter cube. From that you can find rho c. You put it in here, you have alpha, you have beta, you have v by a determined as r by 3, and then from that you find the solidification time to be 641 seconds, almost equal to 11 minutes. Now we have a question. Hope this one is clear. If anybody has any doubt, you can please ask. Mhm. So in that question, I hope you know that A by V, this ratio gives you the cooling characteristics. Okay. So that is the parameter which determines the riser design, the shape of the riser, which indirectly gives you the optimal riser design. Okay. Now, in this question, the third question, I hope it is clear. You have to just find out the casting modulus and then find out the two non-dimensional constants from the given data. Plug it in this equation, and from that you can find the solidification time. That's a simple question. And then you have the fourth question saying cooling rate is uh, dash to surface area by volume, that is the cooling characteristics as per this relationship. Okay, so cooling rate, as per so if you consider these four equations, these four options all contain Kahn's relationship. Okay, so Kahn's relationship is given by x y equal to a by x equal to a by y minus b plus c, where a, b, c are constants given to you from found out by experimental procedures, and then you have to plug in the value of x and y. So where X happens to be the A by V, the cooling characteristics of casting to cooling characteristic of riser, okay, A by V ratio, and Y happens to be the VR by VC ratio, the volume of riser to volume of casting. So using those concepts, you can find out the time using Cairns relationship also. So from Cairns relationship, you can know that the cooling rate becomes directly proportional to the A by V ratio. Okay. So this is linearly proportional. The option C should be correct. Now it says, how is metal mold different from sand mold during solidification? Okay, so what happens is that metal is always having a higher thermal conductivity as compared to sand, right? So the thermal conductivity of the solidified metal may provide considerable thermal resistance. Somebody just used your pen. Don't do that. Huh? Question 1 and 2 has already been discussed, admin. Do you have any problem in that?
Actually, in second case, that casting is higher than riser, na? The volume by area by volume.
Yeah.
So actually, in my opinion, B is correct. I think so. Area by volume of casting is low when compared with riser.
For riser, it should be low.
But option A is less than casting, na? Answer B is correct, I think so, sir. I placed B, but option they are again wrong.
Okay, I'll tell you just a minute.
That one, sir, and first one linear is decreased the temperature when we pour the hot liquid, hot mold, then automatically increase in rising in temperature, na, sir, in mold cavity.
How should it rise?
Temperature rising, na?
How should it rise? The temperature of the molten metal is always decreasing with time, right? You have poured in the hot metal, right? And
Yes,
the mold one is at room temperature. So when the metal gets in touch with the mold wall, it experiences a lower temperature than its room temperature. So what should happen at the interface?
Starting at the interface, it increases the temperature slowly. In solidification stage, it will spread and decreases the temperature.
But you have poured a material at its pouring temperature. Now it comes in contact with a wall which is having a lower temperature.
Okay.
So what happens at the interface?
At the starting interface, the temperature is high, I think so.
No,
sir.
No.
Because it is fully hot stage, no?
The metal is hot, but the mold is cool, right?
Okay. Yes, sir.
So that brings. Do you know the thermodynamics first law? So it says the interface temperature. It didn't ask you the mold wall temperature. If it had asked the mold wall temperature, then you could have said that there is an increase in temperature.
Okay.
So interface temperature reduces to an equilibrium temperature, right?
All right.
And in the second one, yeah, it is correctly given. The cooling characteristics of riser should be less than that of casting. So A by V for casting should be more. Yeah, this is correct.
So A is correct, huh?
Yeah, A is correct.
Okay, thank you, sir.
Yeah. So now we have covered first five questions. We have come to the sixth question. It says determine the solidification time of slab shaped casting. The thickness is given as 18 centimeter. And again, there is no superheat. The sand mold is there. So that's simple. It is just like the earlier one. I just have a change in the shape of the casting, right? So yeah, you have V equal to LBH, and area is twice LB plus BH plus LH. However, in this case, what happens is because this is a slab, a slab is characterized by a larger surface area as compared to its thickness, right? So here you can say that the H value is here you can say as compared to the length and breadth. Okay, the H value is much smaller. Okay, so in the area part you only have length into breadth the first time, the first term. When you divide V by A, you find it almost equals to half of the height of the thickness. Okay, and the rest is same. You calculate the two constants and lambda and beta. You find out lambda from the given values. Theta should be equal to the pouring temperature because there is no superheat as it is given here, you can see. So in that case, you get lambda and you plug it that into the equation for beta, which is 2 lambda by root pi in case of planar casting, or you can say slab shaped casting. And from that you find beta, and then you put back beta in the equation for solidification time, and then you can find the solidification time here is 131 minutes. So compared to the other question, these are same, only the shape has changed, right? Then comes A by B ratio. Okay, so it's the same thing we have already discussed earlier. So it should always be low for considering a riser design. It should be the minimum possible. Okay. If it comes equal to the casting, if it comes greater than the casting by calculating the given specifications, then you should equate this to the casting, if not less. That should be the minimum value. Okay. Now it says determine the dimensions of a cylindrical riser to be used for casting a steel cube of sides. This the volume shrinkage is given as 3%. So such a problem you have to take care of shrinkage allowance, right? So the area of a riser you can find out. It happens to be the lateral surface area plus the top and bottom surface area. Okay. So, and then it is given that 3% shrinkage is there. So our riser has to account for that 3% shrinkage, which can happen as the material, molten metal solidifies, okay, from freezing to room temperature. So we can take care of that. And then the riser should have at least thrice of the shrinkage volume. Okay. And then you have, using that condition, you have that VR as 303.75 centimeter cube. And then equating it to the volume of a cylindrical riser, you find D equal to H. What is this condition? D equal to H. That is the optimal condition for a riser. When diameter happens to be equal to H, it happens to the most optimal riser design, right? You can now find that by differentiating the volume to 0, and in the volume expression you replace one of them, one of the dimensions, and then equate the volume to 0. Differentiate the volume and equate to 0, to find the minimum volume. From that you can find that these happens to be equal to H. So putting it in the equation for riser volume, you get D equal to H equal to 7.29 cm approximately. Okay, now you have to check the A by B or cooling characteristics of the riser, which comes out to be 6 by D as 0.83 centimeter inverse, right? But you can check the A by B for casting, which happens to be zero point 0.4. So what is happening here? So A by B for riser is becoming more than that of casting. We have already discussed earlier that A by B for riser should be low, right? So you just what best can you do is just equate to the casting A by B ratio, and using that you find out the new dimension, right? So from that you find that you should be greater than equal to 15 centimeter. So if you had done it by this and didn't check it by the cooling characteristics of the riser, then you would have got a wrong answer. So if somebody of you has given option A, then I hope you got the catch now. So the correct option should be option C. Now it says casting can get soldered to the mold surface. Okay, when if the surface has no contact resistance. Okay, so that's a pretty straightforward question. If there is no resistance offered by the mold wall, then there should be perfect contact between the molten metal and the mold. Okay, and you can say in other words, it gets shouldered to the mold surface. The last question says, which of the following factors is independent of the direction of crystal growth in an alloy? I think we have discussed it. So material aesthetics, of course, you can very easily say this is what is the design of the material or look of the material that would never determine the direction of crystal growth. That is completely dependent upon temperature gradients inside the during the process of metal processing, then the composition or density of the material, then the variation of the solidus temperatures. Yeah. So option A becomes correct. Yeah. So I hope you all are in clear now about the questions asked in your first assignment. If it's so, we'll now proceed to some questions. Problems. We'll now solve some problems out of the contents taught to you in week 5. Sorry, I was muted. So to start with, I will ask you a simple question, like what are the assumptions made in cutting force analysis through merchant theory? So merchant theory has been taught to you in week 5, right? Then you should be able to answer this question. Also have a look at the assumptions. You should learn these things, right? These are pretty much important. So yeah, so these are the assumptions that the share plane model, an idealized share plane model, which I consider in this question, in this analysis, happens to be good enough to predict the power consumption of the metal cutting process. So this is one assumption that is considered, because uh, yeah, so you have to assume that share plane model gives you uh, the good prediction of the power consumption. Okay, and uh, to start with the particular theory. Okay, otherwise uh, you have to consider some errors while designing or while analyzing the cutting forces. So it is assumed that this share plane model is good enough to get you the power consumption data. Again, the chip above the share plane is considered to be a rigid body moving with constant velocity. Okay, which may not actually be true. Why should there be a constant velocity of the chip? Isn't it? There is no law for that. And also, the chip should not be a rigid body, right? Now, why should it be a rigid body? It is coming out of a material which can be ductile or brittle, which can have deformations. Then the chip should also experience such deformations, right? But for this particular analysis, it is considered that the chip is a rigid body moving at a constant velocity. I hope that's clear. So then we'll move to the next question. Okay, so you have been taught the machining fundamentals. This is a question out of that. You try to uh, get an answer because I hope you have learned that, and trying yourself will improve your problem solving skills. Once I will give you some time for that, I will show you the solution. Okay, let's try. So are you trying? Anyways, let me show you the solution. So this is an orthogonal tool geometry. Okay. So what happens is here the rake angle has been given to be 5 degree. Okay, and then undeformed chip thickness is 0.25 mm. What is undeformed chip thickness, by the way? That is the thickness of a chip before it is pulled out of the material of the workpiece, right? So that is happens to be a T1, and then you have the cut of the width of the cut as 4 mm, and the shear strength to be 350 megapascals, and you have friction coefficient to 0.5. You have to estimate the cutting force and the thrust force. Okay. So you'll be using the merchant cycle analysis in order to estimate forces, and then we can see here that in this question, uh, so in the process of determining such forces, you of course will need an angle called shear angle phi, right? But then shear angle is not provided here. Only angle is given, shear angle, and put it in the equations we derive out of in merchant cycle analysis to get the cutting and thrust forces. So from the angle relationship, 2 phi plus beta minus alpha equal to pi by 2, or in other words, you can find phi as pi by 4 minus half of lambda minus alpha, right? From that, you have been given lambda, the friction angle, and alpha, the rake angle, right? So here you have the rake angle 5 degree, and the friction angle you have to calculate, right? Here the friction between chip and tool has been given as 0.5. Now, if the friction coefficient is given, you know that tangent of that happens to be your friction angle lambda, inverse tangent of that, right? So using that, you find the friction angle to be 26.57 degree. And now rake angle is has been given as 5 degree. So you have to find phi using equation 1, which is pi by 4 minus half of the friction angle minus that of the rake angle, right? You get it to be 34.22 degrees. Now you know that the shear force Fs. What is the shear force? That is the force acting at the shear plane, along the shear plane, right? The shear plane is between the uh, uncut chip, okay, and then the cut chip. Between them, there is always shearing by the tool, and that along that plane we have a shear force. And now the shear force, can be determined as the shear strength into the shear area, right? The shear strength happens to be tau s here in bracket you can see, and then W T1 by sine phi. Of course, T1 by sine phi is the angle, is the uh, actual thickness which comes into consideration, and W is the width of the chip. So using this formula, you can find shear force. Also, from the merchant circle analysis, you can find shear force to be R cos phi plus lambda minus alpha, where R is the resultant, right? Now, this is something not known. So you can just take it out as in terms of the known terms as R equal to the shear force Fs upon cos of phi plus lambda minus alpha. In that case, you can plug it in here in the equation for cutting force. Okay. So putting it back here, you get R as Fs by cos of phi plus lambda minus alpha, which has been found, which we have found out right now. Okay. So this part comes out from the last equation, isn't it? And then we have this part cos lambda minus alpha, right? So using that, you can find out the cutting force. You plug it in all the values of yeah, Fs is also the shear strength into the shear area, which we have already discussed. So plug it in the value of shear force, and then we have all the angles available now. Phi has been calculated, beta has been lambda, beta is equal to lambda here. Okay. So beta is actually a lambda, same thing. And then alpha is the rake angle given to be 5 degrees. Okay. So once you put all these things here, you get the cutting force value to be around 1000 newtons. Now, there has been a second part in which a thrust force has to be determined. So through the same process, you do just replace this the value of thrust force as R. This is a cosine of lambda minus alpha. Here you have sine of lambda minus alpha. You replace R similarly as you have done in the last case. From here you can find Fs by cos phi plus lambda minus alpha. And then Fs again is Wt1 by sine phi into tau. So putting it all these values, you finally get to the value of thrust force as around 400 newtons. Okay, that is less than half of the cutting force. So that is one thing you should note, right? So you can see that this is 1000 Newton, and here it is only 400 newtons. So you should note from here that the cutting force or tangential force acting to the cutting tool is always the maximum of all the forces acting during the machining operations. Okay, so this concept can further be analyzed from here. Here it has been you have got that through your problems that the cutting force is much higher than that of the thrust force. Now here there is a question which says that you have to prove that the cutting force is the or tangential or cutting force. It's the same thing. You can see here. So you can see here that the this is the rotating tool. This is the milling case, by the way. And this is a milling cutter, and this is a slab milling happening here, or face milling, you can say. So this is the cutter direction. So tangential to that, we find the cutting force, okay, Fc, and perpendicular to Fc, we get the thrust force. Now, okay, so in this direction, sorry. So in this direction, you find the cutting force, and perpendicular to the cutting force, you find the thrust force due to the full motion. So you can you have to show why this happens. Okay, so what we will do is just find out we can find out the relations for the cutting force, thrust force, okay, as well as the radial force, whatever is there. And then we can project them in the XY plane, because it is a 3D operation, right? So you project all of them in the XY plane, and then you see which one is coming highest. That way you can show actually that the cutting forces happen to be that the tangential or cutting force happens to be the higher. Okay, once you project that in the XY plane, or in other words, you can say uh, this y direction component happens to be greater than the x direction. So let's move to the next slide. So you can see that this is something, this is an analogy which is showing the actual cutting forces involved in a milling operation. Okay, so if this be the tool, this be a spherical cutting tool. Okay, cutters, you can see. Then you have this one PR in the screen. You can show that this is the PR, which happens to the radial force. Okay, and then as this is rotating like that, tangential to that, you have the tangential force PT, or you can say this is the cutting force too. And then this is the resultant PA. Okay, or you can say this is the axial force. Now you just connect all these forces and project them in the xy plane. This is the px, py. Okay, now you find the relations, right? So you can see that here the tangential force pt is anyways given by a constant c, okay, multiplied by aw and multiplied by ac whole to the power lambda, okay, where lambda is the index number. And then what is ac and aw, you can note that from the diagram. Okay, so this happens to be the thickness of the cutting portion of the tool, right? This is a teeth. Okay, so out in the periphery there are numerous number of teeth. A milling cutter is a multi-point cutting tool. So from that you can find these values, AP. Then this is AF. That is the thickness of the uncut chip. Okay. So what is then this angle? Okay, AXA. That is the angle of contact between the this tool and the workpiece, right? So that way you find PR, considering all the tool geometry effects to be neglected. You can find PR, and that is the radial force. You can also find PZ, that is the axial force. Once you have found them, here eta is the empirical constant, which can vary between 0.1 to 0.3 otherwise. Now, all these are the forces expressions just which has been empirically found by researchers. Now you plug it in the matrix for rotation. Okay, so this happens to be the rotation matrix, minus cos phi sine phi minus sine phi minus cos phi 0, 0, 1 in the z direction, and these are the radial, tangential, and this is the axial force. And then by this is the just projection tensor, projection matrix. Okay, this is the projection matrix, and these are the forces in different directions. You multiply these two to get your forces in the x, y, and z directions. Okay, so that gives you this particular matrix. Now, here you can see what is the value of px. That is minus eta of sine xa cross cos phi, okay, into pt plus sine phi plus 0, right? Okay, similarly, in the y direction, you have this, in the z direction, you have this. So if you take the magnitude, you can see that mod of this y direction force, y direction component becomes the maximum of these three, right? So that way, you can prove that so the force in the y direction happens to be the maximum as compared to the other components of the force. I hope this is clear. This is just to show you why the cutting force happens to be the maximum, or the tangential force happens to be the maximum. Okay, this is a proof, you can say, for that. And then we move to the next question. Okay, before coming to the next question, we'll have some small analysis like that of the chip thickness ratio, which we'll be using much in the upcoming problems. There is a analysis of the chip thickness ratio. There is an analysis which gives the velocities of the chip, velocity of the shear plane, velocity along the cutting velocity, the velocity in the cutting direction. There is another analogy or analysis which gives you the uh, about the shear components, the shear strain, the strain rate. Okay, so now we'll have a discussion on the chip thickness ratio, right? So here you can see that this is an orthogonal. This is a tool just shearing off the chip out of the workpiece, right? And um, you can see that phi, the shear angle, happens to be this angle between the horizontal plane and that of the shear plane, right? And then this is your angle called uh, this one. This one happens to be your alpha. Okay. So you can see here, this one is your alpha, the rake angle. Okay. So do you know what is the significance of this rake angle? Like how rake angle affects the machining process, the parameters, the tool life, the surface quality, how these are impacted by this rake angle thing. Hmm. Okay, so T happens to be your uncut chip thickness, and TC happens to be your final chip thickness. Okay, now T by TC gives you the chip thickness ratio, which happens always to be less than 1 because T is always less than TC, right? Now we'll see the how we come up to this expression for R as sine phi by cos phi minus alpha, and from that how tan phi happens to be this, right? So now here you can see we considered this particular portion, okay, and then we have to just equate the value of AC, the shear plane, which we get out of these two triangles, the ABC triangle and the triangle ADC, right? So if you look at triangle ABC, you can see that sine phi happens to be your AB divided by AC, right? AB is the altitude, this is the base. So AB is again T, the uncut chip thickness, and AC is your space, this hypotenuse, right? AC. And similarly, in the triangle AC and D, you can see that this angle uh, this angle happens to be 90 minus phi plus alpha. How does this happen? So if this is phi, then what is this angle? This angle must be 90 minus phi because this hole is 90. Okay, so this is your 90 minus phi, and this one is your alpha, isn't it? So so 90 minus pi plus alpha gives you angle ACD. Okay, and then you can find sine of this angle is equal to your altitude, which is AD, and the hypotenuse is AC. Gets you to the ratio TC by AC. Now, both in equation, comparing in 1 and 2, right? You can see that sine phi by what is sine 90 minus pi plus alpha. In other words, you can say this is cos phi minus alpha, right? Uh, Taking the ratio of equation 1 and 2, you can see that sine phi by cos phi minus alpha gives you the chip thickness ratio T by TC. So T happens to be the uncut chip thickness, TC happens to be the chip thickness, final chip thickness. That is R. So that way you can find the chip thickness ratio, and then it's simple trigonometric relations. You just have to manipulate it. Okay, so we just cross multiply, that is R cos phi minus alpha equal to sine phi, and then you divide the whole thing by cos phi to get tan phi as R cos phi minus alpha divided by 1 minus sine alpha, right? So that, I hope that is clear. So next we would move to this velocity analysis. If this part is clear. So we turn on the so the velocity analysis is being shown here. You can see that it has two components, the chip velocity, the cutting velocity, and the shear velocity. Shear velocity happens to be along the shear plane. The cutting velocity, is always the tangential velocity along the direction of the cutting tool, and that is the chip velocity. And then this one is your chip velocity along the direction of chip movement. Okay, so all these angles we have discussed. So just you put in the vectors v. This is coming in along this direction. Okay, so you take it on v, and then VC you just take it up from here and put it in this plane. Okay, BC. Sorry. So along this you take up your BC, and Vs is where it remains. Okay, so here you have this angle is phi, you can see here. Okay, and then this one is alpha. So what happens to be this? This is on again your 90 minus alpha, right? Or not? No. So this is not a perpendicular. So so this is your alpha, and then this happens to be your 90 minus alpha, right? Because yeah, so yeah, I was right. So BC is perpendicular to this BS. So whatever is the angle here that gets translated here, it becomes 90 minus alpha. And then this one is simply considering the combination or summation of all the angles to be 180 degree. You find out this one is to be 180 minus 5 minus 90 minus alpha comes out to be this angle, 90 minus 5 minus alpha. Okay. Now, once you have done that, you just put in the sine rule. You know, sine rule that happens to be for a triangle, you pick up any edge and then divide it by the sine of the angle just opposite to it. Okay, so if you take a VC, sine of the angle opposite to it, that is phi. So you have VC by sine phi. Similarly, V by sine of 90 degree minus phi minus alpha happens to be sine of 90 minus phi minus alpha. And then you have Vs divided by sine of 90 minus alpha. Okay, so Vs divided by sine of 90 minus alpha. From that, we just recalculate Vc by sine phi happens to be V by sine of 90 minus this happens to the cos of this, and then sine of 90 minus alpha happens to cos of alpha, right? So this is your velocity relation, right? So this is your chip velocity. Okay, this is your shear velocity. And this is your cutting velocity. So using these things, you have to calculate one in terms of another in the while solving the problems of metal cutting. Okay. So I hope this is clear. Yeah, so books you can refer to Ghosh and Malik, Amitabh Ghosh and Malik book from for manufacturing science. Okay, or it contains both the processes, machining science 1 and 2, or manufacturing process 1 and 2. You can also follow Jikalal's book. Okay. You can also follow VK Jain's book for machining science too. So yeah, you can refer to these books if you want. Next, we'll move to shear strain analysis. Okay. So as the tool starts cutting or removing material, they come out in the form of chips, right? So we take chips in this for rectangular form to to just make some prediction about the shear strain experienced by the upcoming chips. And for that, just consider this particular triangle. Just consider this triangle that is formed in between the chip and the tool and the shear plane, and take it out here. So if you do that, you have this particular angle as the rake angle, okay, rake angle alpha. So this part becomes alpha, this one. Then this is phi, the shear angle, this one. If this is phi, then by alternate angle theory, this should also be phi, right? And then you have this one, this angle is 90 degree because a perpendicular has been dropped from B to D. Okay. And then the unknown angles are these ones, angle ABD and angle CBD. So angle ABD can directly calculate it because this one is phi, this one is 90. So this becomes this whole triangle. All the three angles should sum up to 180, right? So if you just find that out of that, you can see this is 90 minus phi, right? 180 minus 90 minus phi. As simple as that. You get it to be 90 minus phi. Similarly, now this one remains unknown. You consider triangle BD and triangle C. You can see that this angle, okay, this one, what is this? Because if you consider this axis and this horizontal line, this whole thing should be 90. Okay, so I'll show that to you. So this is the axis and this is the horizontal. This angle is 90. This one is phi. So this should be 90 minus phi. Okay, and this one is alpha. So the total angle becomes 90 minus phi plus alpha, right? And so yeah, so where I was in, so we find that this whole angle, the summation of this whole angle becomes 90 minus phi plus alpha, isn't it? You can see it here, and then this one is 90. So this one remains. Let it be some variable and equate the whole to 180. From that, you can calculate the unknown angle, this angle, to be phi minus alpha, right? Now, what happens is you just find out the strain. Okay, so, what is strain? Strain is simply the deformation of a plane perpendicular with respect to a perpendicular plane, right? So the deformation of AD with respect to the perpendicular BD. So when you do that, AD plus DC by BD, you separate because it is bisecting. You separate out AD and DC. Okay, AD and DC and divided by BD. Now you have two ratios, AD by BD and DC by BD. So AD by BD, it is cot of cotangent of this angle phi, right? So you can or you can say this angle, or you can say if you consider this angle, it is a tan of 90 minus 5, isn't it? Or you can say cot of 5. In the other case, DC by BD, so DC is this line and BD is this line. So uh, now this angle we have calculated to be 5 minus alpha, isn't it? So then DC by BD in terms of this angle, this is altitude and this is the base. So you can see that that happens to 10 5 minus alpha. So that happens to be the shear strain gamma, cot 5 plus 10 5 minus alpha. Okay, now we move to the next part. You can see one message in text. Samarth, which notes are you referring to? Are you referring to the slides I am doing now? So these slides, I think, I don't know whether they'll be available in Swayam, but this should be shared. This should have been shared to you. There are some Google Drive links. Okay, then you rather contact the NPTEL team. You write a mail. I think they have shared, right? I think they've shared. There is these videos are uploaded over YouTube, and YouTube link as well as a link to the Google Drive to which the slides are available are supposed to be shared with you all. You can write a mail to the NPTEL team. They will guide you, right? So yeah, so here it says what can be the maximum strain, maximum shear strain. It's pretty simple. You just you do the derivative and equate it to zero to see the condition for the maximum shear strain. It happens when this condition is satisfied, Q5 minus alpha equal to pi by 2. Further, what happens to the minimum shear strain? This question has been asked in GATE also some time back. You know that you can see the gamma equation, the gamma formula. It happens to be cot 5 plus 10 5 minus alpha. You write it in terms of cot whole, cot alpha plus, sorry, this should be phi plus 1 by cot 5 minus alpha. Okay. Now, when alpha becomes 0, it becomes cot phi plus 1 by cot phi. So you can take this as a variable x and just find it, x plus 1 by x. So how do you find arithmetic mean and how do you find the geometric mean, AM and GM? Arithmetic mean is just average of these two you can take. So x plus 1 by x by 2. Geometric mean is just multiplication of the both. When you do that, this term becomes 1 and then x plus 1 by x becomes greater than 2. So what I mean to tell you is for a zero rake angle, the minimum shear strain becomes 2. Okay. So if asked, you can now answer how this thing comes. So now this is another problem for you. I would like you to try to solve it. It says this is an aneroid system, the normal rake system. The tool signature has been showed to you, and this is a mild steel tube. Cutting speed is this, feed rate is 0.4 mm per rep. The chip thickness has to be 0.8 mm, which is T2 or TC, in the ratio for chip thickness. Okay. And you have to calculate the shear strain undergone by the chip. I have just calculated the formula. That's in this one, cot 5 plus 10 pi minus alpha. Okay. Then you have also to find the rate of strain, the strain rate, if the thickness of shear zone is 9 microns. Give it a try. This system has been shown to you. From that, you can find out what happens to be the angles designation, which angle means what. Just try, then I'll show you the solution. So let's check out the solution of this problem. Uh, so it says, yeah, this is a normal rig system, and the tool designation has been shown in the table over there on the right, and then the chip thickness has been 0.8 mm, and the thickness of the shear plane, which is required to calculate the strain rate, has been given as 9 microns. So let's move. So it says that the undeformed chip thickness and the undefined chip width W, which can define the geometry of chip, is given by T1 equal to F cos psi, or you can use it sine of the inclination angle I, or otherwise you can do that by cos psi. So because you know that the summation of the inclination and this side cutting edge angle happens to be 90, right? So using that, you can also do that. So let's suppose that this is F cos psi and the width happens to be D by cos psi. D is the depth of cut. Now psi happens to be the side cutting edge of the tool, right? So here you can see this one is the side cutting edge angle. So which is here from the table, you can see that in this normal rate it becomes the principal cutting edge angle, that is only 60 degree. Okay. So now you find out the uncut chip thickness T1 as a cos psi. Feed is 0.4 mm given. Yeah, you can see feed rate 0.4 mm. You put it here to get the uncut chip thickness value 0.346 mm, and then the chip thickness, final chip thickness has been given to 0.8 mm. So you can take out the chip thickness ratio T1 by T2. Okay. Now you can use this relation which you have derived a few slides back to be tan phi equal to r cos alpha by 1 minus r sin alpha. Alpha is the rake angle. You can find out phi using this particular relation, plugging in the value of chip thickness ratio r to be 25 degree. Okay. Once you have found that, right, you have to find the strain, shear strain gamma. Okay. So this also have been derived right now. Gamma happens to be cot phi plus tan of phi minus alpha. So plug in the value of shear angle 25, which we have found right now. And then the rake angle which has been given as 15 degree. Yeah, you can check it from the table. Yeah, so you can see this is 15 degree, the rake angle. Okay. So you plug in the values to find the shear strain gamma as 2.321. Okay. You know strain is dimensionless, so there is no unit here. And again, the next part was to determine the strain rate. So how to determine the strain rate? You know that anything rate has to be per second. Okay, in as its unit. So here, if you derive the shear velocity PS, we have derived the relation between the shear velocity, the chip velocity, and the cutting velocity. Okay, I told you this should be utilized to get the problem. So the shear standard is given by the ratio of shear velocity and the thickness of shear plane. Okay, which is given in the problem to be 9 microns. So you plug in the value of shear thickness, shear plane thickness as 9 microns, 9 to 10 to the minus 6 meters, in other words, and the shear velocity, which you can find out in terms of cutting velocity, because cutting velocity is given here to be 150 meter per minute. Okay, and you can find out the shear velocity in terms of cutting velocity. How do you find that? So from this relation, you can say what happens to the shear velocity. Sine of, or like from here, you can say cos of alpha. V is the cutting velocity. So Vs becomes cos of alpha divided by cos of phi minus alpha, right? Clear? So you put it back here as V onto cos of alpha, this part. Okay. V into cos of alpha divided by cos of phi minus alpha. This is nothing but shear velocity Bs. And this is the shear plane thickness, which is given as 9 microns. So just plug in the values and find out the shear strain rate to 2.7 into 10 to the 5 per second. Okay. I hope it is clear. You can ask if you have any doubts. If not, I will move to the next question. It's a simple question. The tool geometry is given in the ORS system. These parameters have been given to you. The cutting speed is around 50 meters per minute. Speed is 0.2. Cutting forces, 600 Newton. First force is 850 Newton. You know the difference between these two, I think, by now. And then chip thickness happens to be 0.4 mm. So you have to evaluate the shear angle and the power required for the cut. So give it a try. Okay, so let's end today's session now. We'll meet you in the next session. Right.